So as I mentioned, let's talk about this example problem here. Okay, so what are we looking for? So the problem says that we've got a 2-gallon tank contains R134A. So we have refrigerant 134A. It's a 2-gallon tank. I would suggest we convert that to cubic feet very soon. You can go ahead if you like, if you're writing this along. We've got an initial pressure of 120 pounds per square inch absolute, and an initial temperature of 90.5 degrees Fahrenheit. So it's been sitting in a hot van probably from a repair person's heat and air or refrigerator. Small appliance repair person's come out, and we've got a device that's not cooling for whatever reason. And so we grab this 2-gallon tank of R134A to try to fill up our refrigeration device. And along the way between the house and the van, we drop this tank, and a valve opens, and some of the refrigerant is released into the atmosphere. That's in general, that's pretty bad. It's not something you want to do. If it's ammonia, then that is actually quite toxic, and it's the reason we don't put ammonia in residential devices, because eventually it will leak out. Ruptures happen, leaks happen, and that's quite deadly. So we don't do that. We don't use ammonia for this purpose, but even though it's a really good refrigerant. R134 though, I mean, you don't want to breathe it in, but it's we can put it in residential devices with a little less worry there. But anyway, the valve is opened, some of the refrigerant gets released into the atmosphere, and we've got a pressure valve on this tank, and it tells us after the incident has occurred, I've got a final pressure of 60 pounds per square inch absolute, and the temperature drops to 60 degrees Fahrenheit. We want to know if this occurs within a very short period of time of 3 seconds. I don't know why I put a capital S there. 3 seconds. Very short period of time. We want to know, what are we looking for? Well, we want to find or estimate the mass flow rate that would occur. Now, I'll be honest with you, I don't know if this is a realistic situation. I mean, this is a realistic scenario that you could just have a tank that we accidentally open the valve and release refrigerant into the atmosphere. It's a really bad thing to do, but it can happen. It's feasible. Now, are these numbers realistic? Is this realistically something that we could go from here to this? I don't know. I think the second law of thermodynamics is going to get in our way. I think supersonic flow at the valve is going to get in our way, but let's assume that this is possible, and let's try to figure this out. So we're going to make some assumptions here. They didn't tell us that it's a rigid tank. That would have been helpful, but they didn't tell us that, so I'm just going to assume that it's constant volume. That's a pretty safe assumption, unless the tank got dented. They didn't tell us anything about a dented tank, so let's assume the constant volume. Okay. What else are we going to do? Well, let's talk about what tools we might use to try to figure this out. Okay, we could maybe use conservation of mass to figure out a mass flow rate. That might be helpful, but I don't know that we would have enough information to try to pull that off. But this is a thermodynamics course, so maybe we look at the first law of thermo as a good place to start. Now, I said more than once, the first thing you want to do when you do a first law analysis is to draw your system, right? My awesome drawing skills on display for the entire internet. What is this thing? This is a tank that contains some R134, and this valve opens here, and what happens? What crosses the boundary? Again, we're trying to write a first law of thermo equation. That always tells us that in minus out equals change. So what comes into the system? Nothing. I don't see anything coming into the system. So what actually does cross the system boundary? Mass. I've got refrigerant escaping out of this thing. I've got mass crossing the boundary. I don't see any energy. I don't see any work being done. Especially if I assume the volume's constant. I mean, if this thing got dented, there would be a boundary work term because there's a volume change, but we don't have any information about that. We're just going to have to assume constant volume. So the only thing crossing the boundary is mass. That mass does carry energy, and it's going in the out direction. So first law analysis tells me that E dot mass out is going to equal the change in the energy of our system with respect to time, dE dt. Now I think what we're going to do is we're going to assume, we just talked about in the previous video, uniform flow. And by the way, we are assuming the heat is negligible because we weren't given any information about heat, and we're kind of stuck in a difficult situation of, if I throw a heat term on here, if I say that this thing's absorbing heat or losing heat, that's another unknown I'm probably not going to be able to solve for. So if we assume that heat is negligible, we're basically kind of finding what's the minimum or the maximum mass flow rate occurring. A lot of texts will tell you that if it's over a very short period of time that you should neglect heat transfer. Our text does not normally do that, but this is kind of a situation where that assumption might actually apply. I really don't like that assumption that over a short period of time no heat transfer occurs, but this is a situation where that's a reasonable assumption we could make. So we are going to assume there's no heat. We know there's no work because there's no force and there's no boundary work. There's no electricity. So the only thing coming out of the system is mass. Nothing goes in. So it's minus E dot mass out because it's going out, negative sign. And that's equal to the change in the energy of the system with respect to time. And if we assume uniform flow, we're going to assume that this is approximately a delta E system divided by delta time. We're not worried about every little differential slice of time and every little differential change in energy. Let's just worry about the total energy change over a total period of time. Okay, so what does that look like? Well, first, let's move the delta T over here. So let's say delta T times minus E dot mass out is equal to, and the change in the energy of the system. Okay, well, the change in the energy of the system, there are three types of energy our system could have that could change. What are they? Pause it if you need to. There should be three types of energy a system has that can change. So pause if you need to. This is important. You need to know this. Okay, you got it? Right, so the three types of energy that can change could be internal, right? Change in internal energy. It could also have a change in kinetic and a change in potential energy. We don't have any information about a change in velocity or a change in elevation. We know it gets dropped. We don't know how much, and it's probably, compared to delta U, these guys are probably, the change in potential energy is probably millijoules, and this is probably kilojoules. So it's, or in this case, I guess, fractions of a BTU, and these are BTUs. So it's really, these are going to be pretty, I think we're safe to assume those are negligible. Now, why did I write big U? Steve, why didn't you just write M delta U, like delta little u, like you normally do? Well, what do we know about the mass here? Pause if you need to, but something's happening here. What do we know about the mass? Go ahead and pause if you need to. Okay, so what's happening to the mass here? Again, this is an unsteady flow situation. The mass is changing as well as the internal energy. So both, right, both the mass and the internal energy are changing for this thing. Now, if we look at the energy of the mass out, as we've talked about throughout Chapter 5, this mass has its own enthalpy, its own kinetic energy, and possibly its own potential energy. Now, we talked about, right, so again, this has H, V's, and Z's. Well, we don't have enough information to worry about the Z value, or the potential energy. Now, we talked about what do you do as far as the kinetic energy of the mass out or the mass in, and we say, well, there's is it a nozzle or diffuser? If it is, you have to consider the kinetic energy. Well, it's not those. I mean, it is technically kind of a nozzle, but let's not worry about that. Can we find, are they asking for the V's? No, they're not asking for the speed out. That would be interesting to look at. Can we find it? Well, we don't know the area. If I knew, and that would be really helpful, if I knew the area of the outlet, then I could write this thing up as a second order polynomial as a function of the speed, and we could solve possibly for the speed. It gets pretty ugly. So it's a little more straightforward in the analysis if we just assume that the kinetic energy of the mass out is negligible. So that just simply means that I've got minus m dot times h out, and this is the m dot I'm looking for. So this is the energy of the mass out. As it has enthalpy, we're going to assume the kinetic energy is negligible just because we really don't have another option here. And again, remember, this is just an estimate anyway. And that's going to equal, again, this change in internal energy. So that's m2 little u2 minus m1 little u1, because, again, the mass changes. All right. So which of these can we find? Which of these do we know? What is my unknown? I'm looking for this m dot. So I've got one equation here, only one equal sign. This needs to be my only unknown here if I'm going to use this equation to solve for, estimate the m dot. All right, well, we know delta T, that's given. Can I find, I don't know these masses. That wasn't given. Now, I think we can find these U's, right? I think we can agree we can find these U's. I got a pressure and a temperature at both states. That's normally enough information to find a U value. And what about the masses? How do we find the masses? Well, I would suggest here's a situation where you pause it and you go try to find a way to find the masses. And let's go ahead. Now, if you're back, how do we find the masses? Well, you find the mass based on what you know, the total volume. Right? Now, the specific volume, if the U values change, that also means the specific volumes change. So M1 is going to be the total volume divided by the specific volume 1, and M2 is going to be the total volume divided by the specific volume at state 2, because again the mass is different at the two different states. So here's how I'm going to find the masses. That means I need to know the specific volumes. I've already said we think we can find the internal energies, and that would lead us to believe we can find this H. We already know the delta T, and that leaves our only unknown to be m dot, what we're looking for. So you know, if this were a test problem out of 25 points, yeah, I'm going to put probably 15 points in this block here. So probably 10 points on the first law if it's correct, and then 2 or 3 points, yeah, we'll say 5 in here. Right? So I would probably do 12 and then 3 for getting these right. And you've basically shown me all of the fundamental major equations to find the solution. Then you would want to indicate to me how are you going to find these properties. Right? So we know P1 and T1 we're hoping is going to give us, again, this is 120 psi A and 90.5 degrees Fahrenheit. We're hoping that's going to be enough information to give us U1 and V1. Now what about this H? Eesh. Do I use H1? Do I use H2? What do I use there? I don't know. I mean, there's no clear-cut idea. Some would suggest that since you're assuming uniform flow, you assume that the properties stay constant the entire time. So it starts out at one value and it stays that H value throughout the entire point. So you'll see a lot of solutions will just tell you use the H value. I always suggest, well, why don't you just look at H1 and H2 and see if an average makes sense, or maybe solve it with one H value, solve it with the other H value, and then report a range. And I think any of those are okay because, again, we're doing an estimate. All right, we'll pick up on the next video.